All right, welcome back to Lean Together 2026. We're now going to have Hannah Scholz speak to us about the formalization of CW complexes.
Yes, thank you. Thank you for having me here. So as said, I want to talk to you today about formalizing CW complexes in Lean. And all this work is work that I've done together with and supervised by Professor Floris van Doorn. There you can see already what my plan is for today. So I want to do some motivation. I want to talk to you about the definition, both like intuition and math and Lean, and then I want to tell you about the status of CW complexes in Lean. And last, I want to do a little bit of products, which is mathematically probably the most interesting. Um, oh, I can't move my slides. No. So why should we care about CW complexes? So first of all, the very general class of spaces. So what are basic examples of CW complexes? For example, Rn, the spheres Sn, something more complex CPN, something infinite dimensional RP infinity. So a lot of the basic spaces that you might know. And if you only care about your space being homotopy equivalent to CW complex, you get even more spaces. So for example, all differentiable manifolds. Obviously, the dual question to that is what is not a CW complex? On the left, you can see the hedgehog space that is not a CW complex, but it is contractible. So it is homotopy equivalent to one. And on the right, you can see the Hawaiian earring that is not even homotopy equivalent to a CW complex. And you can kind of see what both of these have in common. They've got like too much stuff close together. So CW complex needs a finite topology to like have room to breathe a bit. And the second part of why they're important is that there are a lot of strong results about CW complexes, even though they're so common. So the first one I've picked out is Whitehead's theorem, which is what they actually were invented for by Whitehead. So if you have a continuous map between two CW complexes that is a weak homotopy equivalence, that means that it induces isomorphisms on all homotopy groups, then you already know that that is a homotopy equivalence. So why is that important? So in algebraic topology, we care about reducing topology questions to algebraic questions. And so this theorem basically tells us that if we know how to work out the algebra, then we can know that something is a homotopy equivalence. And the second theorem that I've picked out is a little bit different. So basically, another important tool from algebraic topology is singular homology. In singular cohomology, basically, it helps you to work out when two spaces cannot be homotopy equivalent. But it's very hard to calculate because you've got very, very big direct sums indexed by huge sets and you quotient out stuff and it's impossible to work out by hand. But for CW complex, you can actually calculate cellular homology instead, and that is actually feasible to do by hand, and so very nice as well. So now let's get to what actually is a CW complex. First, some intuition. So basically what we want to do is to glue n cells together, and an n cell is just a continuous image of an n disk. So you can imagine just an n disk, and it's kind of like floppy and stretchy. And you want it to glue together along the boundary. So for example, you start out with zero cells. You can't stretch them because they're zero-dimensional and they don't have a boundary. And then you attach to those some one cells. So those look like this, like bendy lines, and they have like glue on the ends. And then you keep going like this. Then you can attach two cells. So what can you build with this? For example, the interval. So now the colors have changed. So now the yellow is a zero cell, the green is a one cell. And you can build the interval like this. And you keep doing this infinitely many times, you get the real line. And now I have the two spheres well as an example so that you can see that there's not really like a canonical CW structure associated to a space. So for the two sphere on the left, what I did is I took two zero cells and I connected them with two one cells into a circle. And then I put the two hemispheres on top to get the sphere. And on the right, I just took one zero cell and one two cell, and then I attached the whole two sphere, the edge of that cell, to that one point to get the two sphere. So now the actual math, and this looks a lot, but don't be scared, I'll go through this. So you start out with a host of space X, and you can say that an absolute CW complex on X consists of a family of indexing sets, In, so that is indexed by the natural numbers, and a family of continuous maps, Qin, going from Dn, which here is the closed n-disk, to X, and that is indexed again by the natural numbers in the indexing sets. And we call those characteristic maps. And now we've got a whole bunch of properties, of course. The first tells us that the characteristic maps are homeomorphisms on the interiors. And then we have more definitions. So we say that the image of the interior is called an open n cell, and that the image of a whole disk is a closed n cell. You can see there's like kind of horrible notation going on. So there's, it looks like the closed end cell is the closure of the open end cell, and that is not in general the case. So this is just notation. The second property just says that two different open cells are disjoint. The third tells us that the cell frontier, so the image of the edge of the disk, again, this is unfortunately not actually the frontier of the cell, that this is contained in a finite union of lower cells. And we call this closure finiteness, and this is the C in CW complex. And then property 4 is actually called weak topology, so the W in CW complex. And it tells us that how the topology interacts with the cells. So set is closed if its intersection with every closed cell is closed. And lastly, of course, we want the space to be made up of all the closed cells. And what you might notice is that this doesn't completely fit with our intuition from before of like gluing cells together. Like this doesn't look like gluing, this just looks like the end result. And there's actually a definition that does this gluing thing. I would say that's actually the most modern one. This one that we're doing now is like close to what Whitehead used to do or did. And the one that I saw in my topology class is the gluing one. Basically, you take push-outs. A push-out is basically the category theory way of gluing things. And then all the glued things, you take the union, and in category theory, you call that a co-limit. And why didn't we pick that one? Basically, if you know what a co-limit is, without going too much into it, basically it's a lot of compatible maps. And then also in Lean, of course, you like can't just pretend the maps don't exist just because they're compatible. You like need to trace along them. And I think this is why Flores opted for this definition instead. So what does this look like in Lean? So this is the definition from Mathlib. We say that C is a CW complex in the topological space X here. So this is already different from before, right? Basically, this is like a lot of things in Mathlib, we don't want to restrict to subspaces if it's not necessary. And you saw before the examples I had, so the sphere, the interval, these have natural ambient spaces, right? Rn, and we like Rn and we like the topology of Rn, so why would we restrict, right? The only caveat here is that you need your space to be closed in the ambient space. So something that doesn't work is, for example, taking the open interval that is homeomorphic to R, and so it is a CW complex, but it is not closed in the real line. So you can't consider it as a CW complex in the real line. You have to consider it as a CW complex in itself, which isn't that much of an issue. Then now for the actual fields, you get cell n, so that is the indexing type, so in from before. Map ni is the characteristic map q and ni from before. And again, this is a partial equivalent. We don't want to restrict to subtypes. And this goes, you can see the source is fin into R. So the metric on this actually gives you cubes and not balls. But that doesn't really matter because they're homeomorphic, and also we might change this soon. Source equal tells you basically that the map is bijective on the interior. Continuous on tells you that it's continuous on the whole closed ball, though. And then continuous on sim is, of course, telling you that the map in the other direction is also continuous. Pairwise disjoint is that two open cells are disjoint. Maps to prime as closure finiteness. So you can see for every cell, we pick in every dimension a finite set. And then we say that the sphere gets mapped to like the cells in those finite sets of lower dimension. And then closed prime is weak topology. So you can see we modified this a bit here. So you need to take A and C because, of course, you can't really relate a set outside of your CW complex to the cells. So you need to require that it is in your CW complex. But then it's the same. So you say that the set is closed if its intersection with every closed cell is closed. And last union prime is telling you that the whole space is made up of the whole cells. So the whole C, that is. More things to comment here. First of all, we are not requiring here the Hausdorff property that we did before. So to fully state that a space is a CW complex, you need to also say that it is a T2 space, just simply because this definition in itself doesn't really require it to state. And also this is a class. So originally we didn't have this as a class, simply because this is a lot of data, right? And I also showed you before that a space doesn't really have a CW complex structure canonically associated to it. So why did we then end up making it a class? First of all, there's a practical reason. So I was working for my thesis, I was working a lot with constructions. So for example, the subcomplexes. And then you maybe take a union of a bunch of subcomplexes and you want to say that that's closed. And then you have to do the whole, well, you know, the union of subcomplexes is a subcomplex, and the subcomplex is a CW complex, and the CW complex is closed. And then what was getting very, very long. and just having type class inference do that for you was very, very nice. So that's like the practical side. The philosophical side to this is that I feel like in math we actually treat this often as being a property. You saw that before in the theorems. So Whitehead theorem doesn't tell you, hey, take a CW complex with like these and these cells. No, just cares that the CW structure exists. And I think that is what we do a lot of in math here for CW complexes. So I think it's reasonable to like treat this kind of as a property by making this into a class. Now I want to show you a little bit of a generalization. So you can also add a base set to this, basically saying that you can also attach your cells to like a base set that is there. This I've drawn a little picture. The pink is the base set, and then you can attach your cells to it. And we call that a relative CW complex. And of course, an absolute CW complex is just a special case of this where you set the base to be the empty set. And now what does that look like in Lean? So this is from MATLAB. I know it's a lot of text. The first thing that I want you to notice is that it looks the same again, right? So we've got these two duplicate notions in MATLAB. So I want to talk about that afterwards. But you can see now you've got this base set D as well. And then, of course, the properties have changed a bit. So you can see disjoint base tells you that the open cells are disjoint with the base. In maps 2, we also added that you can map to the base. In closed prime, you can see the topology is also determined by the base. The base is closed, and of course, the base is part of the CW complex. I guess an implementation thing of note here is that D is an outparam. This basically means that type class inference ignores it. The reason for this is that while D is not like completely inferable through C, it is of course a part of it. So all of the lemmas and stuff talk about C and don't typically talk about D. So for example, you want to say, oh, something is closed, and you like hope that, you know, in the back it gets figured out that that is because it is a CW complex. That doesn't work unless you like tell Lean that it like what the base set is. And that was getting very annoying. And so we chose to make this an operam. Of course, the problem with this is that you're kind of guaranteeing type class inference that there won't be different bases lying around. And I think in math, this happens sometimes that you have different bases, mostly when you do a proof and then you have like an inductive argument. But I don't think that it should happen that often that you have like globally instances lying around that you want all the time that have different bases. I'll go more into what issues that got us into now. So, you know, why do we have these two duplicate notions? I like first want to like give an overview of the general situation that I think got us into this problem. So we have a general and a specific definition. So the general definition is relative CW complexes, the specific one is absolute CW complexes. And then basically absolute CW complexes in math are a lot more common in the way that if you say CW complex, you mean an absolute CW complex. Basically because for relative CW complex, you don't really have a handle on the base set, right? That could be anything. So you can't really get that strong theorems out of it. But this means that to me, when implementing this, it was very important that absolute CW complexes felt very, very natural to use, and that you had to care about relative CW complexes as little as possible. Also, the specific case of absolute CW complexes actually provide some significant simplifications because you don't have the space set lying around. So you don't have this union empty, like union D that you had all the time for the relative one. Now you've got just union empty set, which of course goes away. And I think a really important point here is that the base set, so the only differentiating parameter between absolute and relative CW complex is an outparam, which basically means that now type class inference cannot tell the difference. So, you know, why is this an issue? Of course, what I already said, of course, what we started off with doing is just saying, hey, an absolute CW complex is just a relative CW complex with an empty base, right? Would have been shorter, wouldn't have required these two like duplicate notions. What were the issues with that? So first of all, of course, you've got these repeated simplifications. So you've got this union empty set, and you need to take that away all the time. That's not really an issue because we just made a separate constructor, and then you do all the simplifications there, and then you don't care. The bigger issue here was that this produced instances where the base was provably the same, but not definitionally the same. And I want to show you an example of this. So products, very important, was basically the goal of my thesis. So this needed to be good, right? And so if you take the product of two relative CW complexes, but you like take absolute, you consider absolute CW complex as relative CW complex. So you can see your C empty set, E empty set, relative CW complexes with empty base. And then the product has the following types: a rel CW complex C cross E, and then a base set that is, of course, provably the empty set, but unfortunately not definitionally. If you take these two CW complexes as absolute CW complex, then the type is just CW complex C cross E. And then the naive approach, this was just definitionally equal to rel CW complex C cross E empty set. So why was this an issue? So you want often you're looking for the bottom instance, right? Because I told you that's a lot more important. So I'm looking for the instance at the bottom, but type class inference, is running now. The base is an out param, and often it finds the one at the top first, and then it just stops working because it's like, you told me there would only be one instance, and then your proof doesn't compile. And then you need to go out yourself and find this instance, because you can't even tell type class inference to look for an instance that has the base definitionally equal to the empty set, because it's an operam. You just can't specify that anymore. So then it would find the other instance, things wouldn't compile. It wasn't the convenience that I was looking for, right? So this is why we decided to make them not definitionally the same. So have two different notions, and then we have an instance going in one direction, so from absolute to relative CW complexes, and a definition going in the other direction to get rid of this issue. So now I want to tell you what else has been done in Lean. First, what other people have done that I am aware of, at least. So I told you about this categorical definition before. That is also in Mathlib, actually. That is called topcat.relative CW complex. That was originally done by Jia Chenjia and Elliot Dean Young, and then afterwards refactored by Zhou Ryu. And actually, Zhou Ryu has done more things in this direction. So as an example, just because we talked about Whitehead's theorem earlier, actually, he did Whitehead's theorem in model categories, which is kind of a generalized setting. And lucky for you, he's giving a talk tomorrow at this exact time, I think. So be sure to attend that too. And then lastly, for this slide, Robert Maxton has actually proved that these definitions are equivalent. But that is unfortunately, I think, still on PRs. And so now what have we done? So this is a rough overview. The lines of code, I hope I got them correctly. There should be functional lines of code, so without comments and empty lines. So we did the definition and basic properties. That is in Mathlib. We did finiteness notions. So basically you can talk about having finite cells in every dimension, or also the dimension being finite, and then both things at once, of course. And these notions are in Mathlib. I did subcomplexes, so that is partially in Mathlib already, partially in PRs. We did compactly coherent spaces. Those are prerequisite for products. Those are also partially Mathlib, partially PRs. And then, of course, the product is blocked by that. That's basically done, but of course can't be PR'd yet. And then I did examples, most notably the spheres. So the two difference construction on SN. And this still needs a major refactor, so it's unfortunately not close. So lastly, I promised I would tell you about products. Again, we're now back to absolute CW complexes because the situation looks very similar. So you take two CW complexes, X and Y, and then you've got these characteristic maps, right? And what you would hope for this theorem to just tell you, well, then the product is a CW complex. And unfortunately, it's not that simple. Basically, a counterexample is you take two big wedges and you product them together, and then somehow stuff moves too close together again. So again, the topology is the issue here. We need a finite topology. Either your theorem could state, hey, we require that the topology is fine enough. So you say that, oh, the product is compactly coherent. Then you know that the product is a CW complex, and the characteristic maps are just the products of characteristic maps. And the indexing sets are just these unions of the previous indexing sets. Or alternatively, to get all spaces, you could just say, oh, well, let's make the topology like finer afterwards, so that basically you can compact coherentify a space, and then you also always get a CW complex. And this, I know this looks awfully inconvenient, and in practice it's not that inconvenient, because a lot of topologists actually choose to not work in the category of topological spaces, but in the category of compactly coherent Hausdorff spaces, just because it's nicer. It's like Cartesian ghost and these kinds of things. And then you take a modified product like this, and then it's not an issue anymore. And now if you're a topologist, you might be sitting here saying, what is that word? What is a compactly coherent space? Why have I not heard that before? And the reason why you've probably not heard that word before is because this is what I believe you would call a mathlibism. So this word was made up for mathlib. Originally in math, you would call this a compactly generated space or a K space. But if you If you put that into Google, you like get this nice table on Wikipedia, which tells you that there are actually three different notions that have this name, which are not generally equivalent. So our one is the one at the top. So topology that is coherent with its family of compact subspaces. You can see where the name came from, right? Stephen Klontz came up with that name. And then there are two other notions. One of these was actually already in MathLib as compactly generated space, but like we preferred our one because actually for house subspaces, these are the same notion. Basically, they're equivalent. So this is why topologists didn't really care. And we could have gone with the other one, but the first one was like in the definition was nicer for us. So why am I showing you a screenshot from Wikipedia? Actually, because like I believe that this is original Wikipedia research, this differentiation into the three things, which was a fun thing to cite in my thesis then. But I think this is the only space that has like done this differentiation properly. And now, of course, I want to tell you what the actual definition is. So what you do is you take a topological space and you say that that space is compactly coherent if a set in it is open, if for all compact sets C, the intersection with C is open in C. So this is different. No, this is open in C, not like before. And what does that look like? Lean-wise, so we were lucky that the predicate is coherent with was already in MathLib, so that made this very, very easy. So you just say, well, a compactly coherent space is a space that is coherent with its compact subspaces. So very nice. What is coherent with? How is that defined in MathLib? So you say you take a family of sets S. For us, that's the compact subspaces. And then you say that a set is open if its pre-image is open, like with respect to all these sets. So basically the pre-image then is the intersection. And then of course the topology, since you're taking the pre-image, is the subspace topology. So now a quick summary, what should you take away from this talk? So if you had not heard of CW complexes before, then you should take away that they're very important. And you should also take the intuition away from this. So that is CW complex is just a bunch of disks glued together. And then you should also remember that you can't just take a product and it just works out. That is a bit more complicated. And then lastly, I guess for everyone to remember is that some of this is already in Lean. So if you have a project in mind that needs this, you could go ahead. So thank you for listening.